I'm going to be talking about subsystem codes with high thresholds by gauge fixing and reduced qubit overhead. And this is joint work with Nikolas Breuckmann at University College London. So the motivation for this work is that we'd like to see if we can beat the surface code. Now, the surface code is the focus of many efforts to build a fault-tolerant quantum computer, and that's because it has many advantages. One is that it requires only 4 qubit measurements, so the check weight of the stabilizers is 4. It also has a really good threshold compared to most codes of around 1%. So provided that your circuit level errors are around 1% or lower, then as you scale up the size of the system, the logical error rate tends to 0. However, there remain many challenges. One is that it has a huge overhead. In many typical use cases, it requires around 1,000 physical qubits per logical qubit. And even the wait for checks can be too large for some physical systems, and that's because of crosstalk. And also the hardware is still currently above the threshold. So we'd like to see if we can improve the threshold and make it even higher. Now, in terms of reducing the qubit overhead, there's been a lot of promising recent work on constructing new families of low-density price check codes. And so low-density price check codes are quantum codes where the stabilizer weight is bounded above by a constant, and each qubit is involved in a constant number of stabilizers. Examples of families are 2D and 4D hyperbolic codes, hypergraph and homological product codes, and recently fiber bundle, lifted product, and balanced product codes. And all of these families of code improve on the surface code, or can improve on the surface code in terms of their theoretical parameters. However, there are caveats. One of these is that all of them have high weight checks greater than 4, so larger than the surface code. And it's not clear how to schedule them efficiently. And by that, I mean, it's not clear how to construct a quantum circuit that can be used to measure the stabilizers efficiently in a way, because often the gate errors in these measurement circuits can eliminate any advantage that they might have over the surface code. And as a result, no code has previously been shown to outperform the surface code once you take into account circuit level depolarizing noise. In this work, we show how you can reduce both the check weight and the qubit overhead relative to the surface code. And we do that by constructing finite rate quantum low-density price check codes, which have 3 qubit check operators. And we then show through simulations that these can outperform the surface code, even once you take into account circuit level depolarizing noise. We also show how you can improve the thresholds of a wide family of quantum error correcting codes, especially under biased noise models. And we do that by introducing a new technique for decoding and measuring subsystem codes. And this uses something called gauge fixing in software to obtain more useful information. So a quick recap on stabilizer codes. A stabilizer code is defined by a stabilizer group, which is an abelian subgroup of the Pauli group on n qubits. And the code space of a stabilizer code is the +1 eigenspace of the elements of the stabilizer group. The logical group of a stabilizer code is the centralizer of the stabilizer group, a set of Pauli operators that commutes with all elements of the stabilizer group. Subsystem codes are a slight generalization of stabilizer codes. They're defined in terms of a gauge group, and the stabilizer group of a subsystem code is at the center of the gauge group. It's a set of Pauli operators that commutes with all elements of the gauge group and is also inside the gauge group. Essentially, you can just think of a subsystem code as being a stabilizer code where we choose not to store quantum information in a subset of the logical qubits. And the logical qubits that we don't use are called the gauge qubits. So why would you not use all of the logical qubits? Well, these gauge qubits can instead be used to help with syndrome measurement. So in some subsystem codes, the stabilizers are the product of low-weight gauge operators. So you can measure each gauge operator individually and then multiply the results to obtain a measurement of the stabilizer. And some important facts to be aware of. One is that the gauge operators generally do not commute. And so as a result, their outcome is randomized. For example, these might be 2 different ways of measuring a stabilizer as a product of 4 gauge operators. And while their product is fixed, each individual gauge operator is measured uniformly at random, either 1, -1, or 1. Another fact is that because you're multiplying gauge operators together to form the stabilizer, often the actual stabilizer weight itself is higher in subsystem codes, And that means there's less information obtained from each measurement and also more measurement errors. So if one of the gauge operators fails, then the stabilizer measurement also fails. So I'll now introduce our subsystem code construction. And before introducing our new construction, I'll explain it in the context of a code that's already in the literature, which is a subsystem surface code. So we'll start with standard hexagonal toric code, so not a subsystem code. And this is just defined from a hexagonal tessellation of the torus. And the code is defined by associating a qubit with each edge, a z check with each face, and an x check with each vertex. So we have stabilizer weights of 3 and 6. Now we can construct a subsystem code by merging the two vertices on the opposite side of each face. So when we merge two vertices like this, all the stabilizers still commute, but the number of encoded qubits is equal to the number of physical qubits minus the number of independent checks. And so because we've reduced the number of independent checks by 1, we've introduced a logical qubit, and this 3-qubit loop operator is a gauge operator. It's a logical operator of this newly introduced logical qubit. Now, if we merge every face in the lattice like this along the same axis, then we obtain the subsystem surface code. And here's an alternative representation of the subsystem surface code that I'll use in the rest of the talk. Here, each data qubit is associated to each yellow vertex. Here, the yellow circle, it corresponds to a data qubit. These triangle operators are 3-qubit Z gauge operators, and the red triangle operators are 3-qubit X gauge operators. Each Z stabilizer is the product of the two Z gauge operators within a face, so it's a weight 6 stabilizer. And likewise, each X stabilizer is a product of the two X gauge operators in a face. And so this is the subsystem surface code introduced in the reference shown at the bottom by Bravi and co-authors. Now we generalize this to hyperbolic tessellations, and hyperbolic codes are a close cousin of the toric code that have improved parameters, and in particular, they have a finite encoding rate, so the number of logical qubits grows with the number of physical qubits. And now we can merge the 4 vertices. So we've known this tessellation, in this particular tessellation here, is a tiling of a hyperbolic surface with 12 gons, where 3 12 gons meet at each vertex. And we can now merge 4 vertices per face to form these clover shapes. And in that alternative representation I showed you before, where we've got data qubits associated with vertices of this triangulated lattice, we've now got 4 of these 3-qubit X gauge operators in each face and 4 Z gauge operators in each face. So we've now got stabilizer weight of 12, but the gauge weight is 3. So all of the actual check operators that you have to measure are weight 3. And now we've got an improved encoding rate. Now, one thing you've got to be careful of with subsystem codes is that you can multiply the logical operators by the gauge operators, which can decrease the distance. And so the actual distance of the code, once you take into account the gauge operators, is called the dress distance. But what we show is that the dress distance of the subsystem hyperbolic codes is at worst half that of the stabilizer code derived from the same tessellation. And it can be the same. And that's shown on the right here. So the x-axis shows the distance of a subspace code. And by subspace, I just mean a standard stabilizer code associated with a particular hyperbolic tessellation. And the y-axis shows the distance of the subsystem code corresponding to from the same tessellation. And so each dot here that I've just plotted on this graph all of the hyperbolic tessellations that we constructed, so that there are 54 tessellations corresponding to this large circle here. And as you can see, the codes we construct they fall within these two bounds of half the distance and the same distance. And so we can just pick the codes that are near the upper bound. So, for example, this one here is a particularly good code. So how do we decode subsystem hyperbolic codes? Well, we can decode them in the same way that we decode the subsystem toric code. So the hyperbolic codes can be decoded in the same way as the toric code, and that's using minimum weight matching. So how does that work? Well, each qubit is incident to 2 X-type stabilizers. So we can construct a matching graph that contains a vertex for each stabilizer and an edge for each qubit. And then given a syndrome, so a set of defects, we decode by finding the minimum weight perfect matching in V. So on the right, I've now highlighted an example of an error occurring on an edge in green. And that then causes these 2 defects, these 2 -1 measurements of stabilizers at each end of it. Let's suppose you have 2 in a row. This corresponds to a path of length 2 with defects at the endpoint of it. And you correct this by finding the minimum weight perfect matching between the defects, and that's your correction. Now with noisy syndrome measurements, we now repeat the measurements of order L times, where L is the size of the lattice, and then use the difference syndrome. So we take the parity of consecutive measurements. And then measurement errors are now time-like edges. So I've just highlighted in green here an example of a measurement error, a vertical measurement error. And so defects now are again at the end of these paths. And we can have a combination of measurement errors and space-like errors. And so the decoding problem is now to find the minimum weight perfect matching in this 3D matching graph. And I've shown on the right here is a kind of an alternative representation of this 3D matching graph, but considering a single unit cell. I'm just showing you that for reference because I'll come back to this more abstract notation later. And I've open sourced the code for my minimum weight matching decoder as a Python package called PyMatching, which you can find at that link. So I'll now explain schedule-induced gauge fixing, which is a technique that we introduced to improve the thresholds of subsystem codes. So gauge fixing is when you add a commutative subset of gauge operators to the stabilizer group. And essentially, you change your mind about what constitutes a stabilizer. So for example, you can add an X gauge operator from the gauge group into the stabilizer group, and then remove the Z gauge operators which anti-commute with it from the gauge group. And it was originally introduced to implement logical gates. But in our work, we use it to improve the error correction performance of subsystem codes. And before explaining how that worked, let's look at the permanent gauge fixes of the subsystem toric code. If you just permanently add the gauge operators into the stabilizer group, we can have a look at what happens. So without gauge fixing, the X-type and Z-type matching graphs are both a triangular lattice. And that has a threshold with matching of around 6.5% with perfect syndrome measurements. If we fix all of the X-type gauge operators as stabilizers and then remove the Z-type gauge operators, we obtain the hexagonal surface code. Now this has a Z threshold of 15.9% and an X threshold of 6.5% with matching and perfect syndrome measurements. The thing is, we've now just recovered in the subsystem code, we had weight 3 checks, which is great. But as soon as we fix the X-type gauge operators, we've now got weight 6 Z stabilizers, which is more difficult to implement. So and this compares to the surface code threshold of 10.3% under perfect measurements. So we'd like to see if we can somehow take advantage of this improved threshold of the gauge fix lattice, but without having to measure the weight 6 stabilizers. And that's where schedule-induced gauge fixing comes in. And before explaining that, let's just have another look at the subsystem surface code in terms of syndrome measurement in this more abstract notation. So the dots here represent the gauge checks, and the ovals are the stabilizer checks. So this oval corresponds to the product of the 2 gauge checks it encloses. And errors occur on edges. And we can see that the X checks and the Z checks alternate in the standard schedule used for the subsystem surface code. And the values of the gauge operators are randomized, and that's because the Z checks anti-commute with at least one, each Z check anti-commutes with an X check. And so measuring this Z gauge operator immediately after this X gauge operator means that the Z gauge operator will be randomized. However, we can bunch we can sort of collect measurements together into groups of commuting measurements. And so let's say we repeat some of the X checks or Z checks. Well, the gauge operators of the different types generally don't commute. But operators of the same type do trivially commute. So if we repeat a Z check, then we can, after the first measurement, we can treat that gauge operator as if it was a stabilizer, since it's now fixed. And so we can pick various different schedules, repeating the same Pauli type several times, and increase the number of time steps where the gauge measurements can be used as stabilizers, and the average stabilizer weight decreases as a result. And also the average node degree in the matching graph also decreases. Now these are the schedules we use, and this is you put an ancilla in each gauge operator, and then implement the C0 gates in this order. So the one on the left here is from the original Bravi paper, and the one on the right is our adaptation to handle these other types of schedules. And the important thing to note here is that because they're weight 3, any single qubit, any individual fault in the circuit will result in at most 1 data qubit fault modulo gauge operators. Okay, so we simulated several different schedules with circuit level depolarizing noise. And what we find is that changing the schedule already improves the threshold. So on the right here, we show the ZX, the Z squared, X squared, and Z cubed, X cubed schedules. So the ZX schedule is just a standard one from the literature. And we can see that by using these different schedules and using gauge fixing, we can already improve the threshold. And there are two competing effects here. One is that we have longer waits between the bursts of the measurements. And the other is that the average check weight per round is lower. And the vertex degree is also reduced. So the latter two help us, but the first one, the longer weights, don't. And as a result, there's a kind of an optimal number of repetitions, and beyond 4 repetitions, the threshold does decrease again. But it's even bigger improvement when you've got biased noise. So I've already shown you the balanced schedule where you repeat each Pauli type the same number of times, but you can also pick an imbalanced schedule where you measure one Pauli type more often than the other. And here you can now gather more syndrome information about one Pauli type. This is useful for biased noise models. And so these are our results for biased noise. And so we can see that repeating the X measurements increases the performance significantly. And so now we have longer sequences where the X gauge operators are fixed. And so with Z biased noise, this is very helpful. And as an upper bound, we can look at just measuring the X gauge operators only. And that gives us, at infinite bias, that gives us a threshold of 2.2% under circuit level biased, infinitely biased noise models. So we can improve the threshold up to more than 4 times with highly biased noise by using this gauge fixing. And so we can see this as the comparison. With a standard schedule, you have a threshold of around 0.5% to infinite bias. Now we also simulate the performance of the subsystem hyperbolic codes. And to do this, we also construct a schedule to measure the stabilizers and gauge operators. And we construct a schedule from the symmetry group of the tessellation. And as a result, this is the first finite rate code, so the rate of 6, which has an efficient schedule of 4 time steps. And since each data qubit is adjacent to 4 gauge operators, 4 time steps is the best that we can hope for. So it's optimal depth. And also, as discussed before, there are no hook errors because of the weight 3 gauge operators. And this schedule works for various families of subsystem hyperbolic and semi-hyperbolic codes. So I'll now explain how that works. So to do that, let's recap firstly the schedule for the subsystem toric code. And it's a translationally invariant schedule. So we just define it within one unit cell. And each triangle operator has one of 4 possible schedules as a result, because there are 4 gauge operators in each face. So what we can do is we can label all triangle operators that share the same schedule with the same element of the cyclic group Z4. So here, every gauge, all of the northwest ones, we label them 0, and 0 just means it has this schedule on the left here. Now, another property I'll just recap on here is the orientation-preserving symmetry group of the tessellation. So this is a subgroup of the symmetry group of the square tessellation, and it's generated by these rotations rho and sigma labeled on the right here, which rotate 90 degrees around a face or a vertex. And so this orientation-preserving symmetry group has this presentation here. So it's generated by rho and sigma, and it has the relations that rho to the 4 and sigma to the 4 and rho sigma squared are all equal to the identity. So if you rotate 4 times around a square, you get back where you started. The same for a vertex and also an edge. Now, why am I telling you this? Well, we can use this symmetry group to identify each triangle operator. So provided we identify one with the identity element, then every other gauge operator can be identified with an element of this group, which I've labeled on the right here. Now, what that means is that this, the labeling of the schedule with 0, 1, 2, and 3, it actually defines a group homomorphism from the symmetry group, the orientation-preserving symmetry group of the tessellation to the cyclic group Z4. So it's this function f of rho equals f of sigma equals 1 is a homomorphism from the symmetry group to Z4. And now the reason for this is this actually allows us to generalize the schedule to hyperbolic tessellations where we can't use translation invariance. So, and what we show in the paper is that for a tessellation that has degree 4, provided that it emits this homomorphism of f of rho equals f of sigma equals 1 to the cyclic group Z4, then actually we can use exactly the same schedule as the subsystem toric code, and everything will still be, and the schedule will still be consistent and valid in the subsystem hyperbolic code. And so that means that we can construct an optimal depth 4 schedule for the hyperbolic codes. Now, we don't just consider hyperbolic lattices, we also consider these semi-hyperbolic lattices. And here a semi-hyperbolic tessellation is where we tile each face of the hyperbolic tessellation with a square lattice, and we can do this if the hyperbolic tessellation is tiled with squares. And so this has a distance that scales as the square root of the number of qubits, while still retaining the same reduction in overhead. And the subsystem semi-hyperbolic code is derived from the dual of one of these tessellations, the dual lattice of one of these tessellations. So this is the performance of our subsystem semi-hyperbolic codes compared to the rotated surface code. So here, plotted in red, is one of our subsystem semi-hyperbolic codes. And then in green, or different shades of green, are different rotated surface codes. And so our subsystem semi-hyperbolic code contains 338 logical qubits. So we've taken 338 copies of the rotated surface codes for comparison, and used and considered the same number of measurement rounds for both. And what you can see, and the legend here shows the number of physical qubits for these different codes, including both the data qubits and the ancillars. And what you can see is that at around, and this is considering circuit level noise, at around 0.1 to 0.2% circuit level depolarizing noise, our subsystem semi-hyperbolic code uses 4.3 times fewer qubits than the rotated surface code, which has the same logical error rate. And so this is a 4.3 times reduction in the qubit overhead, in this regime, and using the standard ZX schedule. We can also combine the semi-hyperbolic codes with the gauge fixing technique. And so now we get both the improvement in the threshold as well as the reduction in overhead. And we're now looking at a bias. This is just looking at the infinite bias circuit level noise with just an X schedule. And we show that the threshold is at least 2.4% for this family of subsystem semi-hyperbolic codes. And that compares to a threshold of 0.42% for depolarizing noise. There are other applications of the schedule-induced gauge fixing technique. One of them is inhomogeneous schedules, this is where you change the schedule both in space and in time. So in most of the results I showed earlier in this talk, we're only changing the schedule in time and keeping it all fixed in space. But you can do both, and we show that we can increase the Z distance of the subsystem surface code by doing that. We also show that the techniques can be applied to lattice surgery. So lattice surgery is already known can be considered as gauge fixing of some larger subsystem code. So our techniques then makes the connection to how you can actually decode this using the schedule-induced gauge fixing ideas. Now in future work, it'd be interesting to look at decoders for a larger variety of LDPC codes. These include non-CSS codes and different decoders other than matching. And it'd also be interesting to generalize the scheduling of the measurement circuits to use fewer ancillars to reduce the overhead further, to schedule wider classes of LDPC codes, and also to use it to construct more stabilizer codes. So the subsystem codes could also be used as an ansatz to construct stabilizer codes by permanently fixing some of the gauge operators. And this is kind of analogous to what's been done with 2D compass codes and the Bacon-Shaw code. So in conclusion, we've introduced schedule-induced gauge fixing. And so this is a technique that it's all in software and uses the same hardware weight-3 checks. We've shown that this technique can increase the threshold of the subsystem toric code for depolarizing noise from 0.67% to 0.81%. Under bias noise, the improvement's even more dramatic, increasing up to 2.2% for infinite bias for circuit level noise. And the idea is general, so it can immediately apply to many other codes and decoders. We've also introduced a finite rate subsystem code, or families of finite rate subsystem codes with an encoding rate of 6 and weight-3 checks. And it's the first example of a code that outperforms the surface code under circuit level depolarizing noise. And we show that it can reduce the overhead by more than a factor of 4 at circuit level depolarizing noise error rates of around 0.2%. And on that note, thank you for listening. That's the end of my talk.